is pi? You know, pi. But how well do you really know pi? Long ago, the ancient Greeks looked at the circle, the most perfect of shapes, and asked a simple but profound question. How long is its edge compared to its width? They knew the ratio was the same for every circle, yet they had a great deal of difficulty pinpointing its value exactly. In our modern-day view of pi, we write it with a nod to infinity. Expressed as a decimal, pi can never be written down completely. We blur the lines between that which is very, very large and that which is infinite. And that is because we have become comfortable with the idea of approximation through calculus. And in doing so, we get ourselves wrapped up in a real number that may not really exist. From our friends the ancient Greeks, we've got pi to be the ratio of the circumference of a circle to its diameter, and this is always the same value, no matter what circle we choose. Euclid's elements put together Euclidean geometry very nicely, and during the 5th century, the Pythagoreans had been dealing with the notion of irrational measures. As one tries to measure the diagonal of a unit square, one is treated to a non-exact value, a concept that would be a contradiction to the strong belief held by the Pythagoreans that all is number. The irrationality of pi was not considered at this time. It wouldn't be until the 3rd century BCE that Archimedes would use polygons to get an accurate approximation using many-sided polygons. In his method, he would construct circles with a compass, and then inscribe a polygon that is closely approximate to the shape of the circle, calculate its perimeter, and do the same for a circumscribed polygon around the same circle. Then take the average of the two results. Archimedes was able to do this with a 96-sided polygon, and as we increase the number of sides, one can see the average gets closer and closer and closer to the value we know as pi. The Archimedean method did serve mathematicians through time. However, the first time pi met infinity, we think, was through the work of François Viet, a French lawyer and an amateur mathematician, who used Archimedes' method to approximate pi. Among many of Viet's contributions to mathematics, Viet used the tried-and-true method of the Archimedean approximation, of inscribing and circumscribing polygons to determine that pi was between these two values. And to achieve this level of accuracy, what he did was double the sides of two hexagons 16 times, finding the perimeter of the polygons with 393,216 sides each. However, while his value, accurate to 10 places, was the most precise in history to date, Viet's greatest accomplishment was to describe pi using an infinite product. In his 1593 book, entitled Various Mathematical Problems, which was volume 8, Viet broke down his polygons into triangles and found that the ratio of the perimeters between the regular polygon and a second polygon with twice the number of sides was equal to the cosine of theta. And with this identity in hand, he used the half-angle formula and found a way to describe pi as a product. 2 over pi is equal to the square root of 1 over half times the square root of 1/2 plus 1/2 times the square root of 1/2, and so on infinitely long, as what we would call a continued radical representation. Again, this is quite possibly the first time anyone had used an infinite product to describe anything. And it was definitely one of the first steps in the subsequent evolution of mathematics towards advanced trigonometric identities and calculus. Later in 1655, the mathematician John Wallis used a quarter circle and infinitely small rectangles, with which he painstakingly eked out the formula that bears his name, another infinite product, which calculates pi over 2, with a very beautiful pattern. And we note no messy square roots here. One more mathematician worth noting was the Scotsman James Gregory. And before his untimely death at the age of 36 in 1675, he found an extremely elegant solution to calculating the arctangent, leading to a completely new way to calculate pi. You see, the arctangent function can be given by this infinite series of odd powers of x with certain coefficients in an alternating infinite series. It would be 3 years later that Gottfried Wilhelm Leibniz, one of the fathers of calculus, found the same arctangent series and published it along with an important special case. You see, by letting x equals 1 in the arctangent formula, you get pi over 4, and therefore you can get this infinite series to approximate pi over 4, and subsequently pi. So one brings up the question as to whether pi just requires infinity, and are circles merely our mind trying to grasp the fact that everything is finitely measured, and that the continuum in the infinite is really just a figment of our imagination? You see, this circle looks pretty smooth, but if you were to zoom in on its edge, close enough, like under a microscope, you might see it consisting of several atoms, indivisibles, with spacing in between. So does the circle really exist? And for that matter, what about pi? Submitted for your approval, or at least your curiosity, I present you with an unconventional proposal. A portrait of an idea so simple, yet infinitely complex, that you might find yourself feeling a little irrational. This is the Pie Zone. Picture this, if you will, a small cafe on an ordinary street where two old friends meet over coffee. This is Harry, a man of curves, convinced the universe is drawn with a compass and ruled by the infinite perfection of circles. Meet Sally, a woman of exact measure, certain the world is built from countable pieces, and that curves are nothing more than an illusion of many tiny edges. Between them lies more than just a table. It's the question of whether pi, that strange and timeless constant, is a truth of the cosmos, or just a trick of the mind. Two people, one coffee shop, and a number that may or may not exist. Pi is that elusive number that requires the infinite. But does it require circles, is the question. Between the curve that never ends and the edge that never bends, there is something. It doesn't live in the circle. It does not live in the line. Yet somehow, it is everywhere. This is pi. So if smooth circles don't exist, would we then stumble onto pi anyway? Let's think about this while we take a random walk. Imagine a man with an insatiable thirst for knowledge and a stiff drink. This is Charlie, and Charlie has had one too many. He stumbles to get around, leaving the bar. But Charlie is no ordinary man. You see, he can only take one step at a time, and he only moves in one of four directions: left, right, forward, and backward. Each time he takes a step, there's a 1 in 4 chance he will go in one of those directions, but it is completely uncertain as to which direction will be his next step. What's worse, what if he winds up back at the bar? And how likely is this to happen? Perhaps a few animations, or shall I say simulations, are in order for Charlie's drunken random walk. The purple dot represents his place of origin, and as he moves step by step, one wonders if he'll return randomly back to the bar. It might surprise you that this pattern does not repeat itself. It is truly a random scenario. As we examine a few simulations, we'll take note to when Charlie returns back to the origin, that is, back to the bar. This may take a while. One begins to wonder if he'll return at all. Ah, there it is. And as we run simulation after simulation, we notice that it is not that frequent that he does return to the bar. But the probability that he does return to the bar is certain. Knowing the certainty of his return, let's analyze Charlie's situation a little further. Does Charlie ever return to the bar, and if so, how often? Well, by simulation, we already know the answer to the first question. But what is the probability that he will return to the bar? Well, we know that the probability that he will go into one of the four directions is 1/4, or a 25% chance he's going to choose one of those directions. Again, he can only move forward, backward, left, or right. So let's analyze the situation. How frequently will Charlie return to the bar? That is, what would be the expected number of returns? Well, this is where things get interesting. You see, the number of steps needed to return on any trip must be an even number of steps. I'll let you think about why that's true. We will denote the probability of returning to the bar as the probability sub 2n of b. That is, this is the probability of Charlie returning to the bar after 2n, an even number of steps. For a random two-dimensional walk on an infinite Cartesian plane, we wish to find the limit as n goes to infinity of this probability. In other words, as the number of steps, even numbered steps, gets larger and larger and larger, what is the expected value of him returning? How do we estimate this limit? Let's figure it out. So the probability of returning to the bar, or the origin, on an infinite two-dimensional plane starts with the assumption that Charlie takes k steps in the x direction, that would be left or right, and therefore he would be taking 2n minus k steps in the y direction, forward or backward. So to return to the origin, we are going to assume half of k steps in the left direction and half k steps in the right direction, and also 2n minus k over 2 steps forward, or 2n minus k over 2 steps backward. In other words, an equal number of steps in each direction. We can then employ the counting principle to deduce the number of such walks, as we'll use capital N and this summation using the combinatorial notation 2n choose k, k choose k over 2, and 2n minus k choose 2n minus k over 2, where k is even. And this counts all the paths that return to the origin. Now the probability of return is then this number divided by 4 raised to the 2n power. So if we consider estimating this value of 2n choose n, then in factorial notation we get this expression, but in order to approximate the value for large values of n, that is as n goes to infinity, we will use Stirling's approximation for n factorial, which is the square root of 2 pi n multiplied by n over e to the nth power, and this yields approximately 4 to the n over the square root of pi n. Now, applying this to both the x and y directions, the probability of returning to the origin after an even 2n number of steps is estimated to the value of 1 over pi n. And so, by staggering home, or at least attempting to do so, Charlie has found pi. The limit as n goes to infinity of this probability is 1 over pi n. And thus Charlie's rate of returning to the bar is certain. And the chance of returning decays over time inversely, governed by this strange constant. So where were the circles? how did pi sneak in? Well, we make a note that also the sum of these probabilities is the sum of 1 over pi n. And this is the estimate for the number of returns after 2n steps. And since this series diverges slowly, you'll find Charlie returning to the bar infinitely often, but over time, the rate at which he visits will decrease. I suppose those drinks start getting to him. But when did pi sneak in? Well, it came in through Stirling's approximation, and a limit that goes to infinity. This speaks to the deeper concept of pi and our perception of it. And for now, Charlie has imbibed enough in the pi zone. Our attention returns to our cafe, where a simple accident reveals a pattern in the chaos. Alex is the manager of the cafe, where the coffee is hot and the mysteries are fresh baked. Alex is also a toothpick aficionado, and with a slip of hand, Alex finds his toothpicks scattered across the boards beneath his feet. But what appears in the lines are no accident, only a number that keeps whispering at its existence. In this cafe, pie isn't just on the menu, it's everywhere. The boards on the floor form parallel lines that are a distance d apart. The toothpicks here have a length L, and their midpoints are marked in red. Here, the toothpicks are assumed smaller or equal in length to the board spacing. Now, carefully looking at one of the toothpicks, we will apply some dimension and trigonometry to the geometric scenario. Our interest is in how likely it is for a toothpick to land on a line. That is, for the toothpick to hit or cross the line. We notice that the toothpick makes an angle theta with the line, and using trigonometry, we give the rest of the pieces their dimensions. Through this setup, we find that condition to get a hit happens if and only if the value of x is less than or equal to L over 2 sine of theta. With this condition, we will now make a few extra assumptions to make our estimation simpler through symmetry. With L being less than or equal to D, we assume that theta will be uniform on the interval from 0 to pi over 2, where it will take on unique different values. X is going to range from 0 to half the length of our board spacing, and it is also assumed uniform. Theta and x are here independent of each other. Now, how likely is it for a needle or a toothpick to cross? Well, the probability of a hit given a certain angle is the probability that x will be less than or equal to L over 2 sine theta, and that's given to by L over D sine theta. So now we have the probability of getting a hit given a particular angle. Now x here again is assumed uniform on our interval. So one might ask, if we average over all of the angles on this interval, what would be the expected value that we would get? So here, we're going to find that the expectation value is equal to the probability of a hit. And this occurs when we're doing a yes or no experiment. Here, yes or no, it makes a hit. So the expectation value of L over D sine theta on our interval is given by this averaging integral. And it's not a very difficult integral, and it comes out to be 2L over pi d. So the expectation value, which is the probability of getting a hit, is 2L over pi d. The fact that the probability of a hit is 2L over pi d means that 2 over pi is the geometric fingerprint of averaging over all orientations. Pi emerges from the continuity as well as the limits of the integration. Let us consider an empirical example. If we run n drops and observe h hits, we get a sample probability p hat of h over n. And if we set p hat equal to 2L over pi d and solve for pi as a sample of pi, we can calculate this by using 2ln over d times h. So let's assume a certain number of drops and a certain number of observations. We'll assume the case where L, the length of the toothpick, is equal to the distance of the spacing. So the probability of a hit would be 2 over pi, which is approximately 0.6366. If we run 640 observations out of 1,000 drops, and we use our formula to calculate pi, we get 3.125, which is not a terrible estimation. When Harry met Sally in this ordinary cafe for some coffee and contemplation, they were not prepared for what would come next, as they pondered if pi exists on the smallest scales, on the quantum scale. This is Doc, a residential scientist and alleged time traveler. Doc works on the level of the quantum, where weird and exotic behaviors rule, and he's preparing a demonstration in the cafe today that might make you feel a little uncertain. This is a particle in a box. Consider a particle confined to an infinite square well. The particle is confined along a single spatial coordinate direction. Say x is a value along 0 to the length L, where L is the width of the square well. Now, particles have energy. The potential is 0 inside our square well, that is for x between 0 and L, and infinite outside the well, so that the quantum mechanical wave function, which we call psi of x, describing the system is only defined on that line segment. Okay, so that's the setup. V of x, the potential, is 0 when x is between 0 and L, and infinite otherwise. We write that mathematically as a piecewise function. The ground state wave function is given by psi of x is equal to the square root of 2 over L, multiplied by the sine of pi x over L. And in general, for different modes, we include n, where n equals 1 is our ground state. Now, the uncertainty in the position and the momentum can be calculated in the following way. The average position of the particle is given by the expectation value of x, which we denote with the pointy brackets, and that's given by the integral from 0 to L of x multiplied by the squared amplitude of the wave function, and that results in the value of L over 2, or half of L. In other words, what we can interpret this as is that the particle is most likely found in the middle of the well. We then calculate the expectation value of x squared, and we get this expression in terms of L and pi. We then calculate the variance, which is the expectation of x squared minus the expectation value of x quantity squared, and in doing so we get this expression, L squared over 12 multiplied by 1 minus 6 over pi squared, and that's for delta x squared, again the variance in the position. When we calculate the momentum variance, we use the momentum operator, negative I h bar d by dx. It's a differential operator. And we use this to calculate the expectation value for p squared. But the stationary ground state wave function is an eigenfunction of the kinetic energy operator, so we can get the expectation value for p squared to be pi h bar over L quantity squared. Therefore, the variance in the momentum, calculated in a similar way to the variance in the position, yields this expression, and when we find the product delta x times delta p, we get h bar over 2 times the square root of pi squared over 3 minus 2. And if one solves this for pi, then one gets an expression of pi which includes the uncertainty in x and the uncertainty in momentum. So what does this all mean? Well, if we set up an experiment of an actual particle in a box, then we infer its delta p, that is its change of momentum or energy distribution, from the setup. We also infer the delta x from the spatial distribution, and using our formula for pi, we can calculate this value given these particular values from our quantum system. That is, pi is a consequence of the uncertainty principle, applied to a quantum mechanical system of a particle trapped in an infinite well. It emerged from a solvable quantum system without making any references to circles. While you might be questioning your own sanity, there's no question that you should hit that like, subscribe, and notification bell for more videos. They say the circle is perfect, but perfection has never been found in the real world. If the perfect circle does not exist, then what of pi? A number, infinite in its digits, unfathomable in its depth. But if the circle does not exist, why does pi reveal itself in the shadows of infinity? Perhaps what we call pi is not a discovery at all, but a reflection in the mirror of our own conscious minds, chasing the perfection we can never touch. Somewhere, between the numbers and nothingness, lies a constant journey into the pi zone.